This is a mixed audience. I'm talking this. I didn't know what the state of sophistication was. I see Edward Teller sitting there, and then from there you go on the other side of the spectrum. And so what I'm going to do is probably bore most of you. Now, first of all, I'd like to say it's a great privilege for me to address a meeting of an organization which knows the terrible hazards we face with nuclear technology and is trying to do something about it. Now, the search for a long-lived radioactive isotope of carbon began in the early 30s and culminated finally early in 1940 when I was able to get a very weak activity in a probe target, well, a graphite target, which showed, after some collaboration with Sam Rubin and myself, we were able to assign this activity to the isotope mass number 14. Does everybody hear me? All right. I don't mind being stopped at any time in the course of this lecture.
If you move the microphone head a little bit closer to your mouth, it will be better.
That'll take care of the onions. Now, since the discovery of carbon-14, a lot has happened. 50 years has gone by, and it's very difficult to cover. In fact, nobody living can possibly have the hands-on expertise to cover all the applications of this isotope. But I have one slide here, the first slide, please, which will show the gamut of applications. Now, in this slide, I have put down all the things which have happened. As you can see, it covers everything in knowledge from cosmology through the natural sciences, through the behavioral disciplines, and on to the humanities, as exemplified by archaeology and human history. I wouldn't even try to talk about any one of these things in any detail, especially about the biochemistry, which is what I know the best. But I just want to say that if anybody has any questions about what this means, I will talk about it later. It just shows the enormous range of activity in this field that has been made possible by methodologies which are based on the existence of carbon-14. Now, I don't think I need any more. Perhaps I should have the next slide. Hopefully you can read this. This should be an S. I didn't change this. Liebling's law was formulated by A.J. Liebling, the famous journalist, in the connection with something else I will talk about necessary. But what it says is you may have an idea which is totally wrong. And that was what held up the discovery of carbon-14 for 10 years. At a time when everything else was happening, in the decade of the 30s, most of the important discoveries in nuclear technology were made. But carbon-14 was not discovered until 1940. That's still 55 years ago. So if you keep this in mind, I will tell you that we spend a lot of time on the wrong kind of nuclear reaction in trying to make this material. And that brings me to the topic of a little bit of isotopics, which is still not very clear to me. It's now conventional, more or less adequate to describe all nuclei of atoms as made of two fundamental particles, a neutron and a proton. Now, we all know what a neutron and a proton is, do you? Anybody here doesn't know what a neutron and a proton is? Well, if we start with hydrogen, which is the lightest element and the first element, the nucleus of the hydrogen atom is protium, and that is a proton. That is one of the particles. The other particle, the neutron, is gotten, if you add one neutron to a proton, you get deuterium. If you add two neutrons to a proton, you get hydrogen 3. And there the first strange thing happens. Hydrogen 3 is unstable with respect to helium 3. Helium 3 is stable. Now, helium 3 is two protons and a neutron. you would think offhand that there would be some effect of the Coulomb field on the stability of a combination of two protons and neutron as compared to two neutrons and a proton, but it turns out the other way. Now, and there's another important principle which I should mention here, and that is that in the lower part of the periodic system, there are no pairs of isobars. What is an isobar? An isobar is a nucleus which has the same mass number, two nuclei which have the same mass number but different properties. For instance, hydrogen 3 and helium 3 are isobars, and only one of them is stable. And it turns out that for some reason, it's not very clear, there's only one stable isotope in every pair of isobars for the first elements going up to as far as calcium and beyond that. Now, if we keep on adding neutrons and protons, we find there's a certain combination which is stable. Usually it's a combination in which the neutron number and the proton number is the same, or maybe neutrons may have a number which is one more than that of protons. For instance, as you go from hydrogen 3 to helium 3, you come to helium 4, which is two neutrons and two protons. Now, everything is skewed by the fact that this is a fantastically stable combination. And it's so stable, in fact, that you can't add a neutron or a proton to it to cut a stable combination. There is no mass number known, no nucleus of mass number 5, which is stable. The reason for that is the helium 4 is so stable. Then you have to add a neutron and a proton together to have the next stable isotope, which is lithium 6. Now you can notice that in all these cases that the atomic number and the number of protons is the same, naturally. The proton carries all the charge, all the positive charge of the nucleus. So we have lithium 6 so far. If we add another, we can add another neutron now and get lithium 7, which is 3 protons and 4 neutrons. Now, to go to the next unfortunate situation is beryllium. Beryllium is you would think beryllium 8 would be stable, but it isn't. It's unstable with respect to helium, so it falls apart in 2 alpha particles. But you can stabilize it by adding a neutron to it. So you have beryllium 9, which is stable. That has 5 neutrons and 4 protons. Then if you go on to boron, you have boron 10, boron 11, which are 5 neutrons and 5 protons and 6 neutrons and 5 protons respectively. So you see that's how the systematic nuclei is very simply described in terms of these two these two particles. Although of course we don't know why this is. This is just a given. Don't ask questions about that. So we come to carbon. Now carbon at the time, I'm not going back, Edward, this is for you, 1930, when nuclear theory was still more or less in its primitive form. And we are talking about the kind of thinking we did in 1930, and you remember Liebling's law. Now we knew from a lot of, first of all, the apparatus which was most favored and most likely to create transmutations was the cyclotron at Berkeley and other places. And it was used in preference to everything else because you could get large currents of various charged particles. For instance, in fact, deuterium, which gave deuterons being the nuclei of deuterium, these deuterons are especially effective in creating atomic transmutations. Now, if you put a deuteron in and get out a proton, you make a neutron addition, because the deuteron is a neutron proton, and the subtracted proton from that you get a neutron left. So a dp reaction, d deuteron in, p proton out, is the same as putting in a neutron. Now, it was known for a long time that the yields of deuteron reactions came to a very large maximum as compared to the other possible combination, which would be a deuteron in and a neutron out, a d-end reaction. Is everybody following this? So the dp reaction had very high yields, as much as 10 times or 100 times more than the d-end reaction at these low energies. And so it turned out that it became fashionable. It became conventional to use two deuteron beams in making transmutations. That's why we follow Leibniz's law. I thought the best way to add a neutron to a nucleus would be to use a DP reaction because it has a high yield and we have lots of deuterons. Everybody understands that reasoning. All right.
Clear as mud.
It's clear as mud. The deuteron reaction, in which a deuteron goes in and a proton comes out, DP reaction, is the one we use because that was the one that had the highest probability of getting a transmutation. Now carbon, when we come to carbon, we have 6 protons, which is the atomic number of carbon, and we have 6 protons and 6 neutrons for the stable carbon, which is carbon-12. The mass number of carbon-12 is 12. And that's made up of 6 neutrons and 6 protons. If you can add one more neutron to it for some reason, and you still get a stable combination. You get 7 neutrons and 6 protons, and that gives you also a stable nucleus. It's carbon-13. But if you add another neutron, then you get a thing which has 8 neutrons and 6 protons, and that is not stable because the most stable isobar next to it is nitrogen-14, which is 7 protons and 7 neutrons. Now, if you can follow this, 8 neutrons and 6 protons is transforming into 7 neutrons and 7 protons by what process? It's by changing a neutron into a proton. So we thought, well, some of us thought, that all the thing to do is just to bombard carbon-13, which is 7 neutrons and 6 protons with DP, and we get into an extra neutron, and then we get the 8 neutrons and 6 protons, and then we know that it will decay to nitrogen-14 because nitrogen-14 is a stable isotope. That's the kind of reasoning. It's very simple. It's not as complicated as doing your income tax, for instance. But anyway, so we had this. I had this picture. Now, the question is, why did it take so long to find this stuff? And that's where Leibniz's law comes in. I insisted on using the deuterium reaction, the DP reaction, on C13 in preference to another possibility, which was to bombard nitrogen-14 with neutrons and knock out a proton. Then the neutron goes in, a proton goes out, and you get 8 neutrons, 6 protons from the original 7 neutrons, 7 protons. But there was a very good reason for not believing that would work. And I won't give you them because they're all wrong. But I was quite clear that we had to do it the other way. So I have written an article about why this was done. It turns out that about the time that Harold Urey came to Berkeley, he had claimed that radioactive isotopes were no use in biology because there was no good isotope for hydrogen, carbon, nitrogen, and oxygen. Well, within a few months after he said this, there was tritium, and then there was carbon-14. So, but at that time, he had irritated Lawrence sufficiently, so Lawrence called me in and said, find me something that's radioactive in this part of the periodic system. So naturally, I thought, well, the thing to do is find carbon-14 because that's a hole that hasn't been plugged yet, and it should be there. So we began by bombarding graphite, carbon, with deuterons, and the DP reaction on carbon-13 makes carbon-14. That went on for quite a while, many laboratories. In fact, the intensity of this quest was such as rivaled that of the quest for the Holy Grail. I think the pressure was enormous, and somehow we couldn't find the carbon. Now, the reason for the high yield of deuterons, I say this with all due respect to Ed Teller here, was that Oppenheimer and Phillips had come up with the suggestion that the deuteron on approaching, next slide please, the deuteron on approaching a nucleus is somewhat polarized, and the neutral part gets close to the nucleus, closer than it would otherwise, and is detached, and the proton goes off. This process was used to explain, rationalize the high DP yields as compared to DN. Is that, everybody follow that? The deuteron points toward the nucleus, and the neutral end of it, which is neutron, if you could believe that, it would then go into the nucleus without having to go all the way, be captured first. It just would go in as soon as it got close enough, and the proton would go off. So that was the reason for the high yield, and that we were very happy with. And that, of course, buttressed our notion my notion, my notion, that DP reaction was the way to go. Well, many years went by, and we couldn't get any. I had some suspicion that there was something wrong because I had been using graphite targets to make nitrogen-13. Now, how do you make that? You take carbon-12 and you add a deuteron to it, and you cut off a neutron, and you add a proton. That's the reaction which has less of a yield than DP. Well, I was using these graphite targets to make nitrogen-13 for some experiments, and I had a target which had been a graphite target which had been exposed to about 100 microampere hours of bombardment with deuterons, and there was no activity whatever in it. So you could, by a simple calculation, which is again simpler than income tax, and I will show you next slide. Next slide, please. Now I will take you through this. It's not very difficult. The radioactive law states that the number of atoms which changes in time is just equal to the some decay constant lambda times the number present. That's the so-called first order law in chemistry. Now, to get an activity you could see, that depended on the background of the counter, but let's suppose 1 disintegration per second is what you need. To get that, how many carbon-14s do you need? Well, you can figure that out from this reaction here. For 1 year, lambda is equal to, we have another formula which is, it falls out directly from this first order law, which states that the decay constant is equal to some constant divided by the half-life. And we know what the half-life would be. I could assume that it might be of the order of a year. For a year's half-life, the lambda is, and you see what it is, it's 3 times 10 to the minus 8 in seconds, reciprocal seconds. We use seconds as a unit at a time here. That's most convenient. Well, not finding any activity in graphite that had been exposed for 100 microampere hours to DP, and it meant that the half-life must be, the decay constant must be such that the half-life is longer than a year. And at this point, we ran into a lot of trouble. I ran into a lot of trouble because I was told by Oppenheimer there was sheer lunacy to think that carbon-14 would have a half-life greater than a few days, maybe months. And we'd be asking a lot to have months. And in fact, as far as the tracers were, and there was a tracer material we wanted, it was impossible to get a tracer which was better than carbon-11, which happens to be 21 minutes. We wanted to get a tracer which had a long half-life, like a month. A month is fine, or maybe 2 months, but not longer than that. And this thing says that it's at least longer than a year. So I had very deep thoughts about the impossibility of finding this stuff at all. But if the half-life was in the order of 10,000 years, for instance, then the disintegration constant, say, would be, if it was 1,000 years, it would be 10 to the minus 11th. That meant that if you wanted to get 1 disintegration per second to see in a counter, you had to get at least 10 to the 11th carbons, 14s formed. Now, how many carbon-14s do you think you make in this high-powered machine? Well, I'll go through that calculation in a hurry. Let us suppose that we have, according to Faraday, 96,500 coulombs. That's 100,000 coulombs. It's within the accuracy of this whole business. Would give you 1 gram equivalent liberated. So that 6 times 10 to the 23rd atoms would be liberated by the passage of 96,500 coulombs. Well, how many coulombs are there in 100 microampere hours? Well, a coulomb is 1 ampere second, right? All right. So we have. Let's talk about microampere hours, which is the unit we were talking about. Microampere hours would have 3.6 times 10 to the third, 3,600 more deuterons than an ampere second. So an ampere hour is 3.6 times 10 to the third times the number of particles that pass in this time. And how many pass this time? Well, in a second, 1 over 100,000 of Avogadro's number passes, so that gives you a factor of 10 to the minus fifth. Now, if you divide the 6 times 10 to the 23rd by 10 to the minus fifth, and then you get it 10 to the 18th. Now, if you had multiply that by 3.6 times to the third, this is all simple arithmetic, then what you get is that for a microamp per hour, the number of particles that pass in coulombs is about the order of 2.2 or 22 times 10 to the 11th. Now from this we sit down and figure out how many carbon-14s we're going to make. Well, we have bombardments of the order of 100 microamp per hours. That's a lot of current. And that's 10 to the minus fourth of the 10 to the 21 we started with. So we have 10 to the 17th carbon-14 now we made. Now in addition to this, the target nucleus is carbon-13, which is 1% of all of the carbon. So if you just assume that nothing strange has happened, you divide by another 100, you get 10 to the 15th. Now, the yield, I knew the yields of all these reactions, and the yield for the DP reaction was of the order of, say, 1 for every 10 to the 5th deuterons going through a sample would make carbon-14. Well, divide 10 to the 15th by 10 to the 5th, you get 10 to the 10th. Now that's already, if you look at this formula, to get 10 to the 10th carbon-14s, you would see only a fraction of a disintegration per second. So I wasn't very happy about this, and of course there are things you can do. You can change the background, you can do all kinds of things, but the idea was to get within the ballpark of enough carbon-14. Well, meanwhile, sitting on the coils of the cyclotron, absorbing neutrons and doing the NP reaction on nitrogen-14, well, carbon-14 was being made in large amounts all its time. For 10 years it was being made, and nobody noticed it. On one occasion, the bottle of that ammonium nitrate was knocked off the coils of the cyclotron and smashed, and that ended that experiment. So we had, because I was following Liebling's law, which states that the way to make this stuff is to use a DP reaction at C13. And anything else, there were all kinds of good arguments against the neutron reaction, knocking out a proton. And so we went ahead with that notion. Now, about this time, Bob Wilson and I began looking into the distribution of ions in the cyclotron, and it turned out that there's a very large circulating current. Most of the ions that are started in the cyclotron don't get out. They reach the periphery, and then they, unless some means has gotten of taking them out, they just bang into the side of the cyclotron and make neutrons. So there's a thing called the deflector, which a large DC voltage is put on, and that draws the ions out and directs them toward the target area. And you get about maybe 1/10 of all the ions that way, 10% of the ions that way. So we had 100 microamp per hours of bombardment under these conditions, and then we saw that didn't do any good, that we didn't get any activity. So at this point, it was revealed to us that there was inside the cyclotron currents of the order of 10 to 100 times greater at energies which would certainly saturate this reaction. So we devised a simple target. I did this in I'd say, an atmosphere of desperation, because Lawrence wanted this, and there was no guarantee we'd get it. Well, I pasted some aquadag, which is colloidal graphite, onto a copper target and pushed it into the beam. And that way I was able to perhaps intercept practically all of the ions, at least 80% of the ions that were being made in the cyclotron. That gave me several hundred microamp per hours of bombardment. It increased the yield by a factor of 10. Now you'll notice, if you look at this, if you have 10 to the third years for the half-life, the lambda is going to be 3 times 10 to the 11th, minus 11th. If you have 10,000 years, it's already out of bounds. You can't find this enough activity to find anything. So it had to be between 1,000 and 10,000 years, if it was anything. Meanwhile, I was being told by various people I respected that there was no point in looking for any activity at all, because it must be short-lived. Now, the basic analogy to this was helium-6. Helium-6 is made by adding 2 neutrons to an alpha particle. Helium-6 has a half-life of a few tenths of a second. So we would expect carbon-14, which is very similar to helium-6, to have also a short half-life. So by short, I mean a few seconds. So if you didn't see any activity in these old targets, it's because it all gone away. Well, this did not make me very happy, but just to make off I was doing something, I pasted some aquedag on a copper target, shoved it in. And after about 3 days of bombardment, it had taken in several hundred microampere hours. I took it out, and I might say here that I probably was most irradiated person in the world at this point, and I was highly contaminated. I had all of these copper and zinc activities as well as everything else on me, and took this thing out in the form of bird gravel and gave it to Sam Rubin to do the chemistry because I couldn't go anywhere near a counter at that time. When I entered the room, the counter background rose a factor of 100. So. Also, the fact that I'm 82 years old and not wandering too much means that radiation hazards are not very great, at least in my case. So I took us out and we discovered that there was a very long-lived activity in this material, and by simple chemistry it was shown that it was carbon, and therefore it could be assigned with certainty to carbon-14. That meant we had made a nucleus of carbon which had 8 neutrons and 6 protons, which then would decay to nitrogen, which is 7 neutrons and 7 protons, by changing a neutron into a proton. How do you do that? When you do this, you make an electron. That's a negative particle. And so we would have a negative beta emitter, which would make nitrogen-14. Well, but the question was whether we could really believe this, because the activity was the order of background. The actual lambda, the decay constant for carbon-14, is 5 times 10 to the minus 12. Now, there's something up there that's helping me, because it could have been 10 to the minus 13, 10 to the minus 14th, but it happened to be right in the place where it's of some use in other methods, such as dating, for instance. Well, the fact that it was so long-lived, so hard to make, made it appear quite simple, that there was no point in talking about it as tracer at all, because it was too hard to make. You had to have cyclotrons running around the clock all year to make enough C14 to be used in any tracer experiment. And there was carbon-13, which was Harold Urey's province, in which you could use C13, which is a rare stable isotope, as a tracer, and it was good up to a dilution of 100. Now, if you have, at this time, Fermi had not done the self-sustaining reaction. That was 1940. In 1942, 2 years later, the big thing happened, and we discovered a neutron source of enormous magnitude. But at that time, there was no neutron source except the cyclotron itself, and that neutrons are made as secondary particles by cyclotrons. So you could calculate that the amount of C14 made from neutrons coming off from a cyclotron was negligible. If you want to see a calculation, I'll show it to you. Well, so it was with a sense of desperation and rather deep pessimism that I did this final bombardment of the aquedag on the copper. Now, aquedag is a very poor heat conductor. So every 4 or 5 hours I go in and put some more on. It was flaking out and falling on the bottom of the cyclotron, some of it. So I don't know how much I got out, but anyway, what was left was put in after 3 days and nights of continuous bombardment, was put in the place where we could do some chemistry, and I went home and got some sleep. Well, now the activity at that time, when we measured it, was of the order of about background. It was 1 disintegration per second. And the question then was, did we really have something, or it was an artifact of contamination? Now carbon, and this is an argument that will convince chemists but not physicists. Carbon is the only element in the whole periodic system which has an oxide, which is volatile acid oxidizing solutions over and over again. You can volatilize CO2 from acid, but you can't volatilize SO2, SO3, or any of the other elements in the same column the same way. So it was a very simple chemistry to show that it was carbon, besides which the algae thought so. They ate it up like it was carbon dioxide. So when the physicists told us, and I'm a physicist too, but when they told me that it couldn't possibly be a long-life activity, I said, what about the chemistry? And they turned around and snickered somewhat and went off. I must have mentioned that Robert Oppenheimer had his basic training in chemistry, but never took it up. He became a physicist instead. Well, there's a certain hierarchy here of belief, and I wanted to believe the chemistry, and the physics was not in sympathy with it. In fact, at that time, the nuclear theory felt that the best example to use for an analogy would be helium-6, and that'd be very short-lived. The reason we weren't seeing any activity here, nobody else was seeing activity, was because it was too short-lived. It all gone by the time we got around to look at it. The fact that it might be of the order of millennia was just sheer lunacy. It was considered that we were out of our minds to think of a carbon isotope that had a long half-life. Of course, at that time, I regarded the half-life of carbon, which is around several millennia. I made a calculation with several millennia, that it was too long. It was too long for a tracer. We didn't need 2,000 years or 5,000 years. Just a month would be enough. But the character up there, whatever gender it may be, had decided it'd be a long half-life. So we had to take it the way it is. Well, you could show that by if the neutron, there's another reaction going on all this time, which I hadn't mentioned once. I mentioned once before that neutrons can be shown, sontron, as the case may be. The neutrons hitting nitrogen-14 knock off the proton, and that means you replace the proton by a neutron. Well, that's the way to make carbon-14 too, but that was wholly. I had very good arguments against that. The arguments were all chemical. First of all, let's suppose you do make a carbon-14. In what form will it finally end up? It might be a cyanide, it might be a carbon dioxide, it might be a very complicated compound. It certainly wouldn't be in one compound. Well, I was wrong. It's all in carbon dioxide. That was the first thing. It was astonishing. The second thing was that in order to get the neutrons that you needed, you had to have a tremendous neutron source. Now, to make pure carbon-14, you need Avogadro's number of neutrons. You have to have at least 6 times 10 to the 23rd of these carbon-14s to get a pure carbon-14. And that means you have to have a lot of neutrons. And there was no neutron source available at that time. That was 2 years before Fermi and his group showed that the self-sustaining nuclear reaction would produce neutrons at the amount needed to make the NP reaction on nitrogen-14 work. So the whole thing just changed around completely. But in 1940, when I had this thing, I was convinced there was no point in pushing any further. It was nice to have carbon-14, but it was hopeless. It was not a good tracer. And the long half-life was a drawback. Now you see in that first slide that the long half-life is a thing which makes it possible to use carbon-14 in all kinds of activities, which otherwise would be impossible. But at that time I didn't appreciate that. In fact, I thought the carbon-14 was useless. And so it was with, but we had carbon-14, so we stopped I stopped looking for it. I had tried everything else. I tried metastable states of carbon-12, carbon-13. I tried all kinds of things that might be radioactive. But in the end, that was what we were finishing up with. So at this stage, we have an isotope which you can make in very limited amounts by running a cyclotron around the clock for a whole year. Now, that didn't bother Lawrence because all he wanted was to know it was there. Then he began making plans for having batteries of cyclotrons running around the clock, 5, 10 cyclotrons, and of course they'd be shielded by solutions saturated in nitrogen-containing compounds, which would capture all the neutrons, and the chemistry was something else. And so, with that as a possibility, he was going to go to get a patent on the production of carbon-14 from cyclotrons, although the yield was so low. Well, the Fermi discovery changed all that completely. You could put a nitrogen-containing material around and then when you're in the periphery of the nuclear pile and get enough carbon-14 in a day that would be equal to the total amount made by a cyclotron a whole year. Now I remember in this connection that I was at Oak Ridge, and I needed some radioactivity, so I went to the character in charge. This will produce some reaction to Sam, I'm sure. It was not supposed to be known. I wasn't supposed to know they had a nuclear reactor there. But of course it was quite obvious they had one there, but I didn't know how far they'd gotten with it. I thought the yield of neutrons was at the order of maybe less than maybe a tenth of a cyclotron. So I went to this fellow and said, the officer in charge, he's in the Army, and I said, I'd like to have some radioactive phosphorus, or sodium, or anything that's radioactive. So he said, I'll put 5 grams of sodium chloride in our machine, spelled M-O-C-H-I-N-E, and then you will take this stuff, it'll be a few microcuries, and you will have enough to do your experiment. So on the appointed day, I was driven in a car over a lot of muddy, bumpy roads to the X10 factory, and that character came out trembling a tremendous lead casket in which he had this material that had been bombarded, 5 grams of sodium chloride. Well, I said, what's all that lead for? He said, just take it. So I was driven back across this road, and when I was left alone, and so much for security and for the health physics people, I was left alone with this stuff. So I thought I'd take it, see how much it was. So I opened the top of the thing, and there was a blue light in there. Well, that means you have curies. So I put the lid back down and measured the thing with a gamma ray electroscope, and I had the order of 10 curies. Now, I was supposed to get a few macrocuries. He didn't tell me anything about this, and so here I am with all this activity. Meanwhile, the health physics had heard about it, and they refused to let me use it because it was too active. So I just sat there, waited for the paperwork on the health physics, and finally got around. When they finally gave me permission, it was too late. It all had decayed away. But that, in any case, that was the way things were going in those days. So at this point, I was sitting thinking, the cyclotron has an output of neutrons of the order of so much and so much, and this stuff is at least 1,000,000 times bigger. So I know the output of the nuclear reactor in the Clinton works. It's at least 1,000,000 times bigger than that of the cyclotron. So when Lawrence happened to come through at that point, I said to him, Jesus, I said, the cyclotron is passé. There's a machine here that has 1,000,000 times the flux of neutrons. That's so, he says. And the boat goes on. But the character with him wanted to know who told me this. And of course, anybody who can do his income tax can also do a simple proportionality. It was obvious that if you had 10 curies instead of 10 microcuries, you have an order of a factor of 1,000,000. The microcurie is 1,000,000th of a curie. So here I was with this terrible stuff, and I had the biggest secret of the war in me. I had gotten it just by straight calculation, simple calculation. And they want to know who leaked it to me. So that was the way things were then. That was 1930. Well, the Liebig's law states that I should continue to try to make the carbon-14 by the DP reaction on C13. But of course, the way to make it was to put some nitrogen-containing material around the neutron reactor and use the neutrons. And of course, it was possible to make carbon-14 in pure amounts. Now, carbon-14 has a mass of 14, and radium is 226. So the specific activity in microcurie equivalents of a milligram of C14 is about 5.5 millicuries. Now, 5.5 millicuries is 10 to the 11th counts per minute. You can dilute that by a factor of 10 to the 8th and not feel it. So it was quite clear that C13 was no longer in the picture. That we at this point, as I said, this is 1940. I had thought that because of the difficulty in making carbon-14, it would not have any use. You see, you couldn't make it with a cyclotron. Even with Lawrence's optimism, you couldn't run 10 cyclotrons around the clock all year to make what would be done with a neutron reactor in a day. So that's where the problem sat, and that's where we stopped. once you got carbon-14, it's enough that there's the whole science in front of you, because after that, biochemistry was regenerated. It was possible now to follow metabolic reactions without having to guess at them, and the rest of it is history. Now, I'll be very glad to take any questions that are come up in connection with this. Yes.
I'm a novice.
Yes, I.
Need help. Does carbon-14 occur in nature
Yes.
by itself, and
It's made by neutrons, and there are neutrons in cosmic rays.
does it occur everywhere?
You've got it in you all the time.
By a,
You've got it in you all the time. You're a part of it is carbon-14.
and how is it made? I mean, is it?
Well-
it takes you so much trouble to make it. How does nature make it?
By the NP reaction, by the neutron in, proton out reaction on nitrogen-14. See, the cosmic rays come in. There's neutrons, and they hit the nitrogen-14 nucleus.
So it's natural for everything to have carbon-14, and then it decays,
Yeah, that's why you have the dating method.
and then. But
So-
why did you have to make the carbon-14 yourself when it's so abundant?
Well, it wasn't around at that time, and nobody knew that it occurred in nature at all.
So you had to make it
Just to show that it was there. But it was too hard to make.
So
Yes.
carbon-14 is just the natural occurrence in nature.
It's one of the natural
It changes
occurrences.
its form, it decays,
Well,
it
now, by using tree rings, for instance, you can take, there are certain trees which have bristlecone pines in the Sierras, which have tree rings. They go back several thousand years. And they carry carbon-14 because the trees absorb CO2, and they tell you at any given time what the concentration of C14 is in the atmosphere at that time. So and it has varied over time. The calibration of C14 in the atmosphere is done by this kind of chronology.
Does carbon-14 and carbon-13, if it decays to a lower,
No, carbon-13 is stable.
is stable. But is it a different, is carbon dioxide made with the stable as opposed to the unstable?
No, it's made with both.
Is it the same? Is it
It's
the
made
same
with
effect?
C12, C13, and C14.
It's the same chemistry.
Yes, same chemistry. That's the chemist's dogma. All carbon is the same because it has a atomic number of 6. Yes.
I enjoyed your talk, Dr. Kamen, but you're far too modest about the importance of this.
Well, I said
The discovery of radioactive carbon and the other radioactive tracers and their impact on biology and medicine was so great that if you try to it's very hard to calculate how great the benefit has been. I've done some calculations on this to the extent of how much help the use of radioactive isotopes and radiation medicine is. And
well, they revolutionized the field.
my calculation is that more lives are saved every week by these techniques than a Hiroshima explosion lost. So
Well, it's,
to the people who would like to put the lid back on Pandora's box of nuclear energy and nuclear science and they say there are naive people that say we wish you never discovered these things, they would
Well,
have
they're-
to accept an increasing death rate equivalent to a Hiroshima every week, and
That's
most of them, I
right.
hope, would not accept that.
well, I'm glad to talk about an aspect of atomic energy which is not destructive. All morning we've heard about things that are terrible in prospect, but this is one really beneficial aspect of atomic energy. Yes.
What method did you use back in 1940 to detect and separate carbon-14 from carbon-13 and carbon-12?
We didn't separate it. We simply added. We see the aquadag is carbon-12 and carbon-13, and carbon-14 is mixed in with it. Now you scrape it off and you oxidize it to carbon dioxide, and then you go through the chemistry and show it is carbon dioxide.
Does the chemistry distinguish between carbon-14 and
Only to a very limited extent. For instance, it goes as a mass. 14 over 12 is a very small fraction. Hydrogen is different. Hydrogen has a mass of 3, and ordinary hydrogen is 1, so it's 3 to 1, and you have big isotope effects there, but not with carbon.
Did you have mass spectrometers available then?
No. The idea was to get rid of mass spectrometers. The mere idea of a biologist using a mass spectrometer was horrifying. In fact, it was bad for physicists in 1930. Now, of course, you can buy a mass spectrometer and use it as a routine instrument. But then, in 1930, it was a matter of art to use a mass spectrometer. So what I want to finish with, the atmosphere in which the carbon-14 was made was such as to induce a feeling of deep pessimism about its possible application. So if you think about that a while and think what happened afterward, it's quite clear that that's a very false notion. And that's why I think science is so great. You never can tell what's going to happen next.